So for this session, we'll be doing section 2.2, which discuss absolute extrema and also the method of Lagrange multipliers. So in the previous discussion, our last example, we did one example which asked us to get absolute extrema of a function over a domain, and our domain there was a closed and bounded domain. So getting the absolute extrema, or the existence of absolute maximum and absolute minimum, is guaranteed by a theorem that we learned from the lecture. So in here, what I'm going to do is to give solutions to problems where we have a function and there is a domain, particularly a boundary of some region. It could be nice boundaries or nice equation, or it could be some, some graphs which are not really nice, but possible na makuha yung absolute extrema ng function on or along the boundaries of the region we are considering. So, just a quick recall of the method of Lagrange multipliers. So, suppose the extreme values of this function f of x, y exists, and we have a function g, okay, whose gradient is not equal to 0 on the surface g of x, y equals k, where k is some constant. To find the extreme values of this f of x subject to the constraint g of x comma y equals k, what we do is to find the solutions of this system here. So we have the gradient of our function f. It should be equal to lambda times the gradient of the function g for some lambda. And we have the constraint g of x comma y equals k. So we will try to find these values, this lambda, the x, and the y, that will solve this system. Okay? We will have at least two of this. The reason is, one, there should be a maximum, or there should be a minimum, absolute maximum and absolute minimum, unless our function is constant, meaning we just have a flat plane. Okay, so once we have the solutions to this system here, what we're going to do is to evaluate each of them on the function f. And of course, the largest value, that will become the absolute maximum, and then the smallest value, it will become the absolute minimum of the function f, given this constraint g of x comma y equals k. Okay, so let's look at this first example. So we want to find the extreme values of f of x comma y equals 5x minus 3y, subject to the constraints x squared plus y squared equals 136. Okay, so if we just try to sketch this, we have here z equals 5x minus 3y. So basically, we have a plane. Okay, we have the plane 5x minus 3y minus z equals 0. So this plane contains the origin. So maybe we have the three-dimensional guy here. Okay, the three-dimensional space. This is x, this is y, this is z. And then we have some plane that maybe something that looks like this. Okay, so maybe the one, so it contains this origin and this guy here maybe located on the back. Also, say this guy here maybe located on the back of the plane. And then here you have the front. So we have this. And then the constraint here, you have your x squared plus y squared equals 136. It's a circle. So if we look at the domain, on the xy plane, it's just a circle centered at the origin. So you have your xy plane in here, xy plane in here, and then you have a circle centered at the origin of radius square root of 136. So this circle here, it will give a projection onto the plane. It could be, elongated. Okay, so maybe it's elongated. That looks something like this once we have projected that. And of course, if this is in front, this part here will be somewhat solid. Anyway, so maybe it's something like this. Okay, so the projection on the plane will also become circular. If not perfect circle, maybe it's elongated. Maybe looks something like the shape of an egg or an oblong. It could be an ellipse, etc. So it's not really circle, especially if this plane is not parallel to the xy plane. Okay, the green plane here is not parallel to the xy plane. So we will have maybe at some point this is where the absolute maximum is, the absolute minimum is located somewhere here, etc. So that is our goal. We want to find these points here. Okay, these points here on the graph, and once we know these points, we would know the extreme values of the function f. So let's start. We have your f of x comma y equals 5x minus 3y, and your g of x, you let it to be the function x squared plus y squared. And then we solve the system. Gradient of f equals lambda gradient of g, and g of x comma y equals k. But in this case, we will now have, so partial derivative with respect to x, it's just 5 on the left-hand side. For the function g, partial derivative with respect to x, that's 2x. And then we have the lambda, that's why we will have 2 lambda x in here. And then for the y part, we have the partial derivative with respect to y, that's negative 3 here. And then for the function g, we have 2y, and then there's the lambda. And of course, the last equation, it's the equation that we have in here. So we will have x squared plus y squared equals 136. And then from here, we can solve for the value of x, for the value of y, and for the value of lambda. Take note that in here, there are 3 unknowns, x, y, and lambda. And we have 3 equations here. So it's possible to calculate the values for x, y, and lambda. So from equation 1, okay, we can rewrite this equation 1 as x equals 5 over 2 lambda. Similarly, from equation 2, we can rewrite this equation as y equals negative 3 over 2 lambda. Okay, so both x and y are written in terms of lambda. So if we substitute these x and y into the third equation, we'll just have an equation in terms of lambda. So 1 equation and 1 unknown, therefore, we will be able to solve for the value of lambda. And once we have the value of lambda, we will be able to get the value of x and the value of y, corresponding, of course, to the lambda. So in here, we replace this x with 5 over 2 lambda. We replace the y with negative 3 over lambda, and we will have this equation. So if we try to solve this, we will have here 34 over 4 lambda squared equals 136. And then we will have 1 over lambda squared equals 16. And therefore, lambda is equal to plus or minus 1/4. Okay? Now, if we have lambda equals 1/4, then we replace that in here. We'll get x equals 10. And in here, we will get y equals negative 6. So now we have, at this point, we have the point 10 comma negative 6. And then if lambda equals negative 1/4, we replace it. We replace lambda here. And then in here, we will get x equals negative 10 and y equals positive 6. So at this point, the other solution is negative 10 comma positive 6. And there are no other possibilities. There are only two possible values for lambda, and x and y depends on the value of lambda. Okay, so there will be no other possibilities. We got 2 points. Okay, and therefore, we just evaluate the points that we have obtained. For the first one, we have 10 comma negative 6. So we have it here. If we evaluate it at this, we will get 68. On the other hand, for the point negative 10 comma 6, we evaluate it. We evaluate the function f at that point, we will have negative 68. So obviously, this is positive, this is negative, therefore this is higher compared to this. And in fact, this is the maximum value of the function f subject to this constraint. And this is the minimum value of the function f subject to this constraint. So that's the maximum and that's the minimum. Okay. So looking at the solution, the harder part is actually solving the system, because constructing the system, it's straightforward. Lambda f equal gradient of f equals lambda gradient of g, and then your constraint, it's just g of x equals k. So constructing the system, it is straightforward, but solving the system, that's where you will need to do some work. Okay. Next, find the extreme values of f of xy equals x squared plus y squared subject to the constraint xy equals 1. So let us write out all the solutions or the complete solution here. So we have your function f of xy equals x squared plus y squared. And then we can let g of x comma y to be xy. So we have gradient of f equals lambda gradient of g. And of course, you have here g of x comma y. Let's put this as 1. Anyway, it's already 1 on, it's already given here to be 1. So for this, we will have gradient of f, so partial derivative with respect to x. That's 2x on the left-hand side. On the right-hand side, the partial derivative of this with respect to x, it's just y. So we will have lambda y. The other part of the gradient, partial derivative with respect to y. On the left-hand side, we will have 2y. On the right-hand side, partial derivative of g with respect to y, that's x. And therefore, we will have lambda x. And then we have here x, y equals 1. Now, let us just solve this. What we can do is we can write here what we can do is we can use, so let's write first equation, second equation, and then third equation in here. What we can do is for the equation 1, we can multiply that by y. Okay, so we will have from 1, we multiply both sides of the equation by y, we will have 2xy. This is equal to lambda y squared. But here xy equals 1. So this means that we will have 2. This is equal to lambda y squared. Okay? And then what else? We can also, maybe we can also multiply this guy here or this guy here by y. Okay, equation 2 by y. So if we multiply equation 2 by y, we will have 2y squared. This is equal to lambda xy. But then again, xy equals 1. So this is equal to lambda. Okay? And now, look at this. Lambda equals 2y squared. But we have lambda y squared that's equal to 2. So we can solve for either lambda or we can solve for y directly. Okay? So let's see. Combining these two guys here. These two guys here implies we have 2 equals 2y squared times y squared. That's y to the 4. Or this guy here, we will have y to the 4 equals 1. And what does this mean? We can factor y squared. So from here, we can rewrite this as y to the 4 minus 1 equals 0. So we will have y squared minus 1, y squared plus 1 equals 0. And then from here, we'll have y minus 1 times y plus 1 times y squared plus 1 equals 0. And now we have two possible values for y. So either y equals 1 or y equals negative 1. Okay? So this means we will have y equals 1 or y equals negative 1. And in this case, look at this. If we use this equation, whether y equals 1 or y equals negative 1, lambda will just be equal to 2. Correct? So this means if y equals 1 or -1, then lambda will simply be equal to 2 from this equation here. Okay, then let me write it then from star, okay, lambda equals 2. Okay, and then from here we can just use what? We can just use equation 1 or equation 2. In fact, we don't have to solve for this lambda. In fact, we don't have to solve for this lambda because we just want the point x comma y. We could have used this equation number 3. Okay, so yeah, maybe let's use that equation number 3. So let me remove this part. So in here, if y equals 1, then by equation number 3 up there, x equals 1. If y equals -1, then x equals -1. Again, by equation number 3. Okay? Now, let's look at this. We have f of x comma y equals x squared plus y squared. F of, 1, f of 1 comma 1. This is for the point 1, 1. We have here 2. And then f of -1 comma -1. That's again for the point -1, -1. We will have here again 2. Okay, so it seems that we got here both they are of equal values. Okay, they are of equal values, which means what we have could be the constraint here. It lies on a flat part of our function here. Okay, let us try to verify. Let us try to verify that using our GeoGebra. So let me open the GeoGebra. Okay, so in here we have, I want the 3-dimensional graphics here. So let me share that screen. So I hope we were able to write or solve this properly. So f of x comma y equals x squared plus y squared. So we have this what is this? Elliptic paraboloid. Correct? Elliptic paraboloid. Parabola, parabola, and then ellipse. And then let us try to look at xy equals 1. And then let us see. I want to put that. That is not what I want there. I want I want the sketch of the line. How do I write here? X equals y. So xy equals 1 and z equals 0. I don't know if this works. This does not work. Maybe using, let me try this one. X equals 1 over y. So look at that. We have it here. Okay. X equals 1 over y. And then we want to project this to the function. So if we projected this to the function, what will happen? This guy here, of course, this should raise. So it seems that the 0.11, okay, let's look at the 0.11. The 0.11, it's somewhere 0.11, it's okay. So 0.11, it's somewhere here. And then when it's projected, it will be somewhat here. So yeah, this is the 0.11 here, but I cannot see the projection itself. But if we look at the top view, it seems that, how do we get this one? If we have here, maybe I'll try this one. I'll evaluate f of x, comma 1 over x. What? So it gives me the same thing. It does not give the projection. Okay. But it is being cut. So if anyway, so you have the graph or this part here. Okay. That x over x equals 1 over y. So we see that in here. And then remember when we talked about the, at least during the lecture, when you talk about this Lagrange multiplier, you look at the level surfaces, correct? You look at the level surfaces, and then you look at which level surface will intersect or will kiss the graph of the function g. So maybe at the level surface f equals 2, that's the one that will kiss the graph of the function g. So I'm not really good at using this app here. So what I actually want to do is I want to project. I want to project it in here, okay, and see what will give me here. Look at this. Your function, this is the graph of the function, and this will go up and up infinitely at infinite z. The circles will just continue to increase. Right? You have this graph. You have the graph of this hyperbola here. Let me go back to this so I can see you, or I can show you what will happen. So we have the graph. We have the graph of your elliptic paraboloid. So you have this elliptic paraboloid here. Okay. And then, of course, on the XY plane, you have your, you know, we have, so let me just put this. Yeah, this and then this part here. You have your, the graph of your, the graph of the XY equals 1. Okay. When you project this guy here, okay, onto this graph here, what you will get is the following. So you will have this. It will trace also a part of that hyperbola. Okay? Can you imagine that? When you trace this part here, okay, on, or when you project this guy here on your elliptic paraboloid, it will trace this part. It will trace this graph here. Okay? And you will notice, you can observe that, you will notice that this will be the lowest point. And it will only continue to increase. This guy here will just continue to increase. That's your f1, 1, which is equal to 2. Similarly, at the backside, on the backside, okay, on the backside, there's also a trace that will look something like this. And it will just increase, you know, as your x and y increases, as your x and y increase on this part. And the lower point that you will see, that's also your 2. So in fact, with this constraint here, 2 is the lowest value. That's the absolute minimum. Okay? Now, the question is, why can't we get a maximum value? The reason is this guy here, this is not bounded. Okay? This is not bounded. So we cannot get a maximum. Remember the extreme value theorem. Your domain must be closed and bounded. Okay? Okay. So let's have the last example that I have in here. Find the extreme values of h of x, y, z. I think this one, I got a typo in this part. Should be x squared plus y squared plus z squared. Okay? So x squared plus y squared plus z squared. Let me think about that. No, I think it's like that, x squared, y squared, z squared. And then the constraint is this guy here, x squared plus y squared plus z squared. So this guy here. So I think this one here is correct. So in any case, we'll just have to solve this problem using the one we know, using the method of Lagrange multiplier. So in here, we have your, so let's say your h of x, y, z. you have x squared, y squared, z squared. Then you can let your g of x, y, z, so function of three variables, x squared plus y squared plus z squared. So in here, we will have the gradient of h. We need to solve this system. Gradient of h equals lambda gradient of g. And then your g of x, y, z, this is equal to 1. So take note, we have functions with three variables. Okay? And then including the lambda, we will have 4 unknowns. So let's start. Partial derivative with respect to x. We will have here 2x y squared z squared. That's on the left-hand side. And then on the right-hand side, we'll just have 2 lambda x. For the second equation, we have 2x squared x squared y z squared. And then on the right-hand side, we have 2 lambda y. For the third equation, we have 2x squared y squared z. And then we will have here on this side 2 lambda z. And then the last equation, it's x squared plus y squared plus z squared equals 1. Okay? Okay. So equation 1, equation 2, equation 3, and then we have the equation 4. From equation 1, we'll just have y squared z squared equals lambda. We divide everything by 2x. Of course, that's assuming x equals or x is not equal to 0. Okay? That's assuming x not equal to 0. And then we can also assume y not equal to 0. So we have x squared z squared equals lambda. And then we have here z not equal to 0. If we assume that, x squared y squared, this is equal to lambda. Okay? And then what do we have in here? Of course, the fourth, it's just x squared plus y squared plus z squared equals 1. Okay, so how are we going to solve this system? What is the best way? We can have okay, so let's try to do it this way. Your y squared, that's equal to lambda over z squared. Okay, y squared, that's equal to lambda over z squared. And then we use the third equation that we have in here. We will have this implies we have here x squared times lambda over z squared. This is equal to lambda. And therefore, we'll just get x squared over z squared equals 1. Or you have x squared equals z squared. Okay? And then What will we have in here? We can use this equation here and substitute it here. And therefore, we will just get we'll just get in terms of y and z. Okay. Another one in here. So we have here x squared equals z squared. And then what we can do is, if we use these two equations here, okay, y squared z squared equals lambda, x squared z squared also equals lambda. If I divide this by this, okay, also we have x squared z squared divided by y squared z squared. This is equal to lambda over lambda, which is equal to 1. And this gives me x squared over y squared equals 1, which also tells me that we have x squared equals y squared. So x squared equals y squared also equals z squared, which therefore gives us what? So this means you have, using now the last equation in here, okay, we will have 3z squared equals 1, and therefore z equals 1/3, and therefore z equals plus or minus square root of 3 over 3. Okay? And then we have the value for z squared. And then we can solve for x squared, also for y squared. You know, so if we have, if z equals square root of 3 over 3, okay, then x squared, this is equal to 1 over 3. So we will have here x equals plus or minus square root of 3 over 3. Okay? And then in addition to that, your y also will be plus or minus square root of 3 over 3. So there are two choices for your x, two choices for your y, two choices for your z. So you will have 8 triples here. Okay? Also y equals plus or minus square root of 3 over 3. Okay? But in any case, we have the function h of x y z, which is equal to x squared y squared z squared. All of them will just have 1/3. Okay? They will just have 1/3, and therefore your those cases, so h, so this implies that h plus or minus square root of 3 over 3, square root of 3 over 3, again plus or minus square root of 3 over 3, whatever case, we will just have 1/3 to the power 3. This is 1 over 27. So again, similar to our explanation earlier, we'll just get one value for this. Okay, we'll have one value for this, and what? It's minimum or maximum. We need to determine that. We can conclude actually that this will give us maximum. Okay, this will give us the maximum. Simply because let's analyze this further. Let's analyze this further. The constraint is x squared plus y squared plus z squared. Okay, now let me go to the next page. So if x equals 0, y equals 0, and z equals whether plus or minus 1, then your h will be equal to 0. Correct? And that's lower than 1 over 27. Okay? So you can do all other combinations here. Okay? You can do all other combinations and you will get h equals 0. So from here, we can conclude that that max value is 1 over 27. Okay, mean value is actually 0. Look at this. This is always greater than or equal to 0. X squared plus times y squared times z squared. Positive, positive, positive if they are all positive. If at least one of them is 0, then it's 0. So mean value, it's obvious to be 0. And this mean value, you can get it from a lot of points actually. Just take one of the variables to be 0, and then you have the y squared plus z squared equals 1. So that's a circle. Okay, that's a circle with x equals 0. So you can have infinitely many points that will give minimum value 0. And then the max value here, we have calculated to be this guy in here.